So let's take a little bit a closer look at how we deal with thermal interference in the Netherlands. For closed-loop systems, we use a simplified finite line source solution where we calculate correlations that are entered into an Excel spreadsheet that is available as a free tool. For more complex situations, we can use the finite line source solution directly. We'll talk about that a little bit later. There are a number of questions when we do this approach. For instance, what is actually a neighbor? Do we need to consider all the systems in the Netherlands, or do we need to consider only the next door neighbors? Another question is whether the method that we employ is applicable, for instance, with regard to groundwater flow. And another question is how do we deal with possible effects between open loop systems or between open and closed loop systems? Now, first of all, in the methodology for assessing interference between closed loop systems, there is a decision schedule that you can see on the top right, where we take a look at the different limits that the solution has, for instance, the total number of systems, or whether groundwater flow can have an effect. And then at the end, if we decide that we can use the simplified tool, we can do the calculation and find out if there is any potential risk of thermal effects, yes or no. If there are any risks, then of course we need to adjust our design to account for the temperature effects between the systems. This has to be carried out for every permit application. And basically what we do is we do allow a small cumulative temperature effect of up to about 1.5 Kelvin lowering of temperature during heating. This would equate to about 5% maximum effect of the efficiency after 30 or 40 years of operation, which is deemed acceptable and in any case is within the limits of measurement that can be done with a heat meter, for instance. We've been using this method since about 2013 when the legislation became into effect, and in total there are about 20,000 new systems installed every year. So you can imagine there are a huge number of thermal effects being calculated. And fortunately, we have a national database with some principal information like heat extracted and heat injected and length of the boreholes for every system in the Netherlands. For closed-loop systems, this simplified methodology is based on the finite line source solution, where we first of all make it system independent by calculating the heat extraction as a function of the kilowatt hours per meter borehole length per year. So every system is, let's say, projected on a 1 meter length borehole, although in the calculations different depths are considered because, of course, the finite line source does take into account the total length of the borehole itself. We did a parametric run with different boundary conditions with regard to heat extraction and heat injection rate and with regard to total length of the borehole. And from this parametric run with boundary conditions, we had about almost 2,000 different solutions. And from these solutions, we extracted correlations that we can enter in an easy way into an Excel tool that is then used to do the calculations very, very rapidly. The basic FLS finite line source methodology was further validated with a numerical model because we do it slightly different than in a normal design procedure, and the error analysis of the correlations are used to limit the boundaries for this simple tool. Now, the first question that we have is what constitutes a neighbor? What we did is calculate the temperature effect as a function of the distance, which you can see in the graph. And we see that for a worst case scenario, so a system that has a very high heat extraction rate at a distance of about 60 meters, we still have a temperature effect of around 0.1 K, 0.1 Kelvin temperature lowering. Now, as a temperature sensor does not have a better accuracy than this, we took this as a conservative limit of distance. So if you can have an effect at 60 meters, you can still have some neighbors further away also affecting that system. So the search radius for small systems in our case is 120 meters. In fact, when you want to also consider larger systems, larger than 70 kilowatt underground power, underground thermal capacity, then the search radius will be 350 meters. And if you do not have any big system in that search radius, you can continue with the search radius of 120 meters for smaller systems. The other question that we have is, can we apply this method when there is a bit of groundwater flow? Now, groundwater flow, of course, depends on several factors, amongst others also the gradient of groundwater that we have present. Other factors, including affecting the effect that it can have on the ground heat exchanger, are the amount of heat being extracted and the energy balance. You can imagine that a system with a high energy balance will experience smaller effects of groundwater flow, especially with regard to affecting downstream systems compared to a system with very little energy balance. So we calculate the average Darcy groundwater flow along the whole borehole heat exchanger, and then we look in this table for the specific heat extraction rate and energy balance and the total number of systems in the evaluation, whether we can or cannot use the simplified tool to calculate thermal effects between systems. Basically, what we do here is look at whether the directional effect given by the groundwater flow has a big or a small effect on the calculated temperature difference without groundwater flow. So again, this was based on a large sensitivity analysis of many different groundwater flow situations. At the end, if we can use the simple tool, we enter it all the data that we have in the blue part of the Excel spreadsheet. So the coordinates of the system, the central coordinate, the length of the borehole, the total length of the boreholes, and information about the energy extracted, energy injected, and overall performance factors. We can do a maximum of 20 systems and a maximum of 6 boreholes per system. There's also a limit on the heat extraction rate and limited range of soil thermal conductivity values, all related to the parametric sensitivity analysis that we did and the error analysis of the correlations that we use compared to the actual solution of the finite line source. The results for 4 systems here are shown in a little table, giving the temperature effects between all the systems. And if we then add all the individual temperature effects together, we can see that system 1 and system 2 actually have a larger temperature, lowering of temperature than the 1.5 Kelvin allowed. So in principle, these designs need to be adjusted. Now, the idea is that if you design your own system, suppose I design system 1 and 2, I should compensate for all the effects between system 1 and 2, and also I should compensate for the effects that system 3 and 4 that are already present in the vicinity may have on my systems. The existing systems themselves may have a little bit of room, temperature margin in their design. For instance, if they're designed for 0 degrees, but the actual temperature calculation shows that with a slightly larger length of installed borehole, the temperature is plus 0.5 degrees. I have plus 0.5 degrees margin to allow other people to also install the system in the vicinity. Now, there are some limitations to this tool, as I already mentioned, and there are a number of alternatives. One of them is ITGBS Pro, which is the Pro version of the system that does use the direct finite line source solution and therefore does not introduce any additional error due to the fact that correlations are used. Now, between closed loop and open loop systems, it's more complicated because we would need to do a complicated thermal hydrological model, taking into account both the pumping of the wells, open wells, and the heat transport due to conductivity. Fortunately, we have a study in the Netherlands where we looked at this in more detail, and that study showed that the only way in which you can have negative interference is when the closed loop system is located in the warm well of the open loop system. You can imagine that a closed loop system in the cold well will lower the temperature of the cold well, thereby enhancing the cooling potential of the open well. So there is a positive effect. The closed loop system in a Open loop system will experience higher temperatures than designed for, because even in a cold well, the temperatures are higher than during heating in the closed loop systems in general. And only if the closed loop system is in the warm well, it could lower the temperature of the warm well and thereby affect the temperature negatively and the efficiency in a negative way. Between open loop systems themselves, so open loop to open loop, we can use the thermal and hydraulic radius to assess possible potential effects, potential negative impact of one system on the other. And these thermal and hydraulic radiuses we can calculate either numerically or with analytical solutions. A minimum distance between wells can be, let's say, prescribed. And also, when we are going to look at planning systems, you could think about zoning of warm and cold wells. If you put all the warm wells and all the cold wells of a system in the same area, then they may even strengthen each other instead of interfering with each other. So here we see an example of two open wells, a cold well and a warm well, with, indicated by the little red and green dots, closed loop systems in the area as well. So the first calculation that we do to assess this is only the open loops are active, the closed loops are not active, and we then take a look at what the extraction temperature of the warm and the cold well are. If we then activate the closed loop systems, you can see that the cold well becomes completely a different form, and the warm well is also deformed by the cold generated by the closed loop systems in winter. The question now is whether the water extracted from the warm well has a significantly lower temperature in this scenario compared with the previous one if there is no closed loop system active. Usually a small temperature effect on the order of 0.5 Kelvin is allowed in this case.